AI and AI and granular soil predicting relative density with cutting edge AI. Predicting the relative density of granular soil using cutting edge AI techniques is a very interesting and practical problem in geotechnical engineering where relative density is crucial for soil consideration. Relative density of relative density is a measure of the compactness of granular soil compared to its loosest and densest states. It impacts soil strength, stiffness, permeability, and overall behavior. Traditionally, relative density is estimated from lab tests, example, standard penetration test, cone penetration test, or empirical correlations, which can be time consuming and sometimes inaccurate. Why AI is predicting relative density? AI models, especially machine learning and deep learning, AI models, especially machine learning and deep learning, can complex complex patterns from soil data. They can handle nonlinear relationship between soil properties and environmental factors and relative density. Using AI can reduce the need for extensive lab testing and speeding up site characterization. The traditional methods for predicting relative density, laboratory testing, right? standard standard procator test, relative density test, direct measurement by preparing soil samples in the lab and determining minimum and maximum avoid ratios, time consuming and expensive disturbances during sampling affects accuracy, not always representative of in situ conditions. In situ testing, standard penetration test (SPT) provides an n-value blow count related to soil resistance, empirical correlations related n-value to relative density. Cone penetration test CPT measures tip tip resistance and slip friction used to estimate the soil parameters including relative density. Empirical correlations between relative density and SPT CPT data, often based on limited datasets, regional soil types, high variability and uncertainty, nonlinear and complex relationships are not well captured. Challenges and limitations are data variability, and specificity. Soil properties vary widely with location, mineralogy, and history. Empirical correlations are often site specific and don't generalize well. Second one, sample disturbance. Lab samples may be distributed during extraction or transport, changing density. In situ tests can be affected by operator skill, equipment, and environmental factors. Third one, limited parameters and simplified assumptions. Many empirical models consider only a few parameters, example n value and fines content, ignoring important factors like moisture content, particles particle shape, and soil fabric. The soil behavior is non-linear and complex. The traditional models are often linear or simplicity. Fourth one, time and cost. Laboratory testing is slow and costly, limiting the number of samples. In situ tests need specialized equipment and experienced personnel. These challenges, these these challenges matter. Take safety risk, economic impact, and efficiency. AI revolutionizing granular soil prediction. First one, handling handling complex nonlinear relationships. The traditional empirical models often assume a simple linear or monotonic relationships. AI models like deep neural networks, gradient boosting, can learn complex nonlinear patterns from multivariate soil data without explicit formulas. Second one, data integration and fusion. AI can simultaneously process heterogeneous data sources, laboratory measurements like grain size, moisture, and void ratio, geophysical data, resistivity and seismic, soil soil imagining data SCM, micro CT scans. Integrating diverse data improves prediction, robustness, and insight. Third one, a reduction in time and cost. AI models, once trained, predict a relative density instantly from input parameters. This can reduce dependence on expensive, time consuming lab and field tests. Fourth one, improved generalization with sufficient training data. AI models can learn from a broad range of soil types and conditions. This reduces the need for site specific empirical correlations. And real world examples like neural networks trained on CPT data outperform traditional correlations in estimating relative density. Random forests used to predict soil compaction quality from SPT and moisture data. CNNS applied to microstructure images to classify soil density classes. AI-powered digital twins of soil sites for real-time simulation or, and autonomous soil investigation. Drones using AI for data collecting and analysis. Integration with BIM building information modeling for infrastructure design optimization. The benefits of AI powered prediction in granular soil relative density. First one, higher accuracy and reliability. AI models learn complex nonlinear relationships in soil data beyond simple empirical correlations. This leads to more precise and consistent predictions of relative density. Second one, faster decision making. Once trained, AI models provide instantaneous predictions from input data. Third one, cost efficiency. It reduces the reliance and expensive and labor intensive laboratory and field testing. Fourth one, data integration and multimodal analysis. AI can integrate diverse data sets, SPT, moisture, imaging for holistic soil characterization. Generalization across soil types and sites. AI models trained on large varied data sets can generalize well to different soil types and geographic regions. Uh, Multitask predictions. AI models can predict multiple related soil parameters, example shear strength, permeability, simultaneously enabling comprehensive soil behavior models. Real world impact. Neural networks trained on CPT data outperform traditional correlations in estimating relative density. Random forests used to predict the soil compaction quality from SPT and moisture data. The CNNS applied to microstructure images to classify soil density classes. AI models integrated with T sensor data for continuous ground condition monitoring. Benefit and impact. Higher accuracy. the safer, more economical, the geotechnical designs, the faster predictions, accelerates the projects, the timelines, adaptability, work across diverse soil types and regions, data-driven insights, improves understanding of soil behavior. The future outlook, AI powered digital twins of soil sites for real time simulation, autonomous soil investigation drones using AI for data collection and analysis, integrating with BIM building information modeling for infrastructure design and optimization. AI supported relative density prediction is been applied in large scale infrastructure projects, high rise buildings, foundations, risk assessment for area prone to soil, optimizing earthwork and compaction process. Safer foundations with AI. AI transforming geotechnical engineering by making soil analysis more predictive, efficient, sustainability, and safe. And the last conclusion is the prediction of relative densities in granular soil is critical for safe and cost-effective geotechnical engineering. The traditional methods, while while foundational face limitations including high cost, time consumption, site-specific applicability, and unlimited accuracy due to their simplified assumptions. The advent of AI is revolutionizing this field by enabling the integration of diverse soil data, uncovering complex nonlinear relationships, and providing rapid, reliable predictions. AI powered models improve accuracy, reduce cost, and accelerate decision making, all while offering better generalization across soil types and sites. As geotechnical engineering increasingly embraces AI, future developments like real-time monitoring, hybrid physics, AI models, and digital soil twins promise to further enhance soil characterization and infrastructure safety. Thank you.